Thanks a lot. Thanks a lot. And thanks to Angelo for the invitation. It's always a pleasure to be here in Pisa. Yes, this is the title of my presentation, but after preparing the slides, I decided to revise a little bit the title. I will be talking about machine learning and spectral method for training machine learning devices. So, as you know, neural networks are widespread. They are used in a lot of, in several applications. And I will do some self-advertisement to guide you through different applications. So first of all, we have been applying machine learning to devise novel superconductors. And this led us to discover two new minerals which display a superconducting phase. And you can find information about these results in this paper. We also applied machine learning techniques to neuroscience, and in particular, we tried to resolve single-cell transcriptomics with spatial resolution in a work that was carried out together with colleagues at MIT at the Broad Institute in Boston. And then, just to jump to a completely different field, we applied the neural networks method to cosmology, and in particular to a model-free fitting of the Hubble diagram, including supernovae and quasars data. And this allowed us to reveal tension in the lambda CDM model. So neural networks are widespread. They are widely used in very many different fields. So what is a neural networks? I'm just gonna give a very brief introduction to neural networks. So these are just tools to efficiently approximate functions. So imagine you have an input function that is here labeled with x, just a vector, and then you have an output vector y. They can have different dimensions, and the two are linked by function or its approximation to a neural network. As you know, neural networks, and in particular deep neural networks, are inspired to the functioning of the brain, according to the standard picture, and they're used for classification and regression problems. I will mention application to the classification task. So this is the typical architecture of a feed-forward neural networks. You have several nodes, which are actually the computing units, and these nodes are arranged in layers. So you have successive layers which are processing the information, and the information is passed from one layer to the next via a linear transformation, and on top of each neuron, each node of the network, it is processed by a nonlinear filter. So you see these strange letters. This is meant to identify the nonlinear function, and this is just one element of a matrix that I intended to label with a W. But then going with a PowerPoint from a Mac to a Windows, then you get this strange symbol. So I just apologize for this, but I will try to guide you through the equations with words. So nonlinear function, which is applied on each node, and this is just one element, one connection of the linear transformation that is bridging successive layers. So just a little bit more into details. Consider a data set. So a set of examples, input target, X and Y, and you can have a different replica of these pairs. And then what you do, you have, for instance, to classify these items. And to explain the main idea, I will make reference to a very famous database, which is called MNIST. So here the idea is that you have images of handwritten digits ranging from 0 to 9, and you have to train the machine learning, the deep neural network, to recognize, to classify images. This is the task that you wanna implement. So for instance, here we have a strange 5, and the machine learning, the device has to learn to classify properly number 5. So you do this, you actually read through the image, pixel by pixel, and then you get a vector. And this vector is supplied as an input to this black figure, which you don't see very well, but it is supposed to represent a network. So in principle, here You don't see it, but you have one layer, another layer, and another layer. And then the information is passed to the first layer and then processed. I'll come back on this later. And then eventually you see a yellow dot in the end. This yellow dot is node 5 of the final layer. And this means that eventually the network has been able to recognize the number 5 that you have supplied as an input. So how you do this? You have to train the network, and training the network amounts to find some parameters. And these parameters are these strange entries that I was commenting upon later. So the entries Wij of some matrices which control the linear transformation from one layer to the next. How you train the network, so how you fix the parameters, you have a loss function. And the loss function is simply measuring the distance from what you get as an output and what you would get if the machine was working properly. So the idea is to minimize the loss function, and to do so, you assign parameters. And once the machine has learned the task that you are providing, then you have an estimate for the parameters that are governing the evolution of the system. So here you see an animation. Again, the colors are a bit unfortunate with this light, but you see that now I'm supplying number 7, and across layers something is happening. Yellow colors appears, and eventually number 7 is recognized at the exit layer with the 7th node, which is being colored. So how you do this? I was already telling this before. Linear transformation and nonlinear mask. And this was an attempt to write down this in math, but of course, because of the swap from Mac to Windows, everything crashed. So doesn't matter, and don't focus on the equation. Is not really an issue for what I will tell you later. So which are the key aspects that I want to bring into evidence? 2 points. First of all, you train on a reservoir of images, and these are composing what you call the train set. And then eventually, once the machine has learned how to carry out the process that you have been implementing, then the neural network is capable to generalize beyond the train set. So if you supply other images that have not been seen during training stages, the machine is able to generalize and properly classifying the new images that you are supplying. And that's the interesting point that makes a neural network so useful in a wide number of applications. So a few remarks are mandatory from my point of view at this stage. So first of all, the number of parameters that are involved in neural networks are really huge, really a lot. The reference to brain that I was evoking before, in my view, is purely evocative. Indeed, the brain is a dynamical unit. There are a lot of dynamical processes that are ongoing, and neural network in their current implementation, the version that we all use nowadays, are just static optimization problems. So actually the link is a bit vague, at least in my view. Neural networks are just black box, so you just have to trust them, and you have no handle on what they actually see. And this is a problem if you want to trust them. And then eventually they are very good at solving just one task. But if you take a trained network and you try to supply the network that has been trained another task, then the network won't cope with the first one, and will just process the second that you've been proposing. So the question that I'd like to address, and that we are trying to address, and on which I will briefly report in the following, are the ones that you see here highlighted in this box. So first of all, is it possible to identify a subset of key parameters for learning? I told you that there are a lot of parameters, by far too many for the task that you are willing to deal with. So is there a subset of parameters that you can eventually identify? And I will try to convince you that the answer is yes. And then eventually I'd like to bring back the dynamics into the game if time allows. So to answer both these questions, I will try to use spectral methods. And this is the sort of general umbrella under which I will present my results. So spectral learning. So which is the idea of spectral learning? It's very simple. You will see. I'll just try to diagonalize matrices. That's the main idea. But to do this, I have to deal with the square matrices. So what I want to do, here you see I have a feed-forward network just 4 layers. The first layer has N1 elements, N1 nodes. The second N2, N3, and L, assuming that the network is as deep as you wish, but now L is set to 4, just 4 layers. And then I have a total number of nodes for the network I'm studying, which is the sum of all these elements, N1 plus N2 plus N3 plus N4. So the idea is to go from this representation to an equivalent representation using vectors that contains information on the activity on each node of the collection. So this that will become a vector in a second, it's a vector of n, capital N elements. So the sum of all the nodes that belong to the system that you're studying. So what's the idea? The idea is that you supply to this network an input vector, which has size N1. You see, I've been coloring in green the first N1 elements, and then the first bunch of elements of the vectors that will photograph the evolution of the system has been inserted. So this is my starting vector. And then this is a vector of size n, as I told you before. I can transform this vector via a linear transformation, so via a matrix, which has size n times n. And the peculiar shape of the matrix I'm dealing with is depicted here, is basically made of zeros, except for one block diagonal part, which is sitting below the diagonal filled with zeros. And then if I apply this matrix to the vector that you see on the right, that's what you're gonna get. So you transport information from this level to this level. And now you are activating the nodes of the second layer. And this is the linear part of the transformation, which is now implemented via a square n times n matrix. Then you go with the nonlinear part of the analysis, which I won't comment about. I'm just focusing on the linear transformation, and you keep on going. So you have to deal with a set of matrices which have this peculiar shape to handle the linear transformation from one layer to the next. Okay? So what's the next step in the story? I would like to diagonalize this matrix. I'm in trouble because I have zeros on the diagonal. So I implement an innocent modification, which, however, will prove crucial. So this AK is the matrix that is linking layer K to layer K plus 1. That's what I would like to eventually achieve, just the diagonal form of this matrix, lambda K being the set of eigenvalues. But I'm in trouble because here I have zeros on the diagonal. So what I'm going to do, just to modify, I'm going to modify slightly the matrix I'm dealing with by inserting numbers on the diagonal. And these numbers are just trivial ones all over the diagonal, except for a bunch of eigenvalues, those that are colored in green here, which will act as training parameters. Now I can diagonalize this matrix. This is the matrix of the eigenvectors, the diagonal matrix of the eigenvalues, which is non-trivial now. And then eventually the inverse of matrix phi k, and this is nicely written in terms of phi k. So you don't have to deal with inversion of matrices which are computationally cost. So this analysis is discussed in this paper, but what's the aim of this analysis for machine learning training? Well, actually, by going in the spectral domain, so from the direct space to the reciprocal space, you can actually study a different optimization problem. So the linear transformation now is written in terms of eigenvectors and eigenvalues, and you can, of course, repeat this layer by layer, and eventually, this is what I just want to briefly discuss, you can study an optimization problem by calculating gradients with respect to the eigenvalues, or if you want, eigenvalues and eigenvectors. And the claim that I will try to make is that eventually, just focusing on the eigenvalues, you have enough information for training the neural network and for getting nice results out of this. Remark that the eigenvalues totals in n, while the number of parameters that you train with standard approaches is of the order of n squared. So there is a substantial gain in playing this game. So the first thing that I can tell you, and you will have more proofs of this in the paper that I mentioned, is that you get very good accuracies by only training the accuracies for the trained machine, by only focusing on eigenvalues. And I just comment on one figure because, I mean, it will take time to go through all the tests that we made. I just ask you to concentrate on the red and the blue curves. These are the accuracies that we measure for the same database that I was presenting before. This database made of the hand-written digits. It is called MNIST. And these accuracies are reported as a function of N2, the size of the second layer of a deep neural network, just for the sake of illustration. And this in red is the accuracy that you get by studying the optimization on just eigenvalues. And then the blue line is what you get by anchoring the learning in direct space and enabling the system to optimize a number of parameters that is identical to the number of eigenvalues. So in a way, this tells you that eigenvalues are special in a way. And if you focus on eigenvalues, you get much better accuracies than the one that you get by assuming an identical number of free parameters in direct space. Instead of insisting on this and trying to convince you that this is a nice way to go for, I just would like to discuss an application that we call trimming, spectral pruning, which amounts to compactify the network, making the network smaller by using the concept of the eigenvalues. So everything boils down to this formula that you can trivially derive from the relation that I wrote before. So each element, Wij, each connection between successive nodes belonging to different adjacent layers, each connections, Ij, can be written in terms of eigenvectors and eigenvalues, and this is not surprising. The nice thing is that in this region with non-trivial eigenvalues, the eigenvalues can be split into two parts. One set of eigenvalues refer to the starting nodes, index j, and the other eigenvalues refer to the arrival nodes. So you can really link eigenvalues to specific node of the neural network. And why this is interesting? Because actually with these eigenvalues, indeed, what you do is to modulate the signal on the departure node or on the arrival node. And so in principle, you can assume that these eigenvalues are in a way ranking the importance of the nodes. If a node is unimportant in the computation that is being performed, then the eigenvalue will be small, about 0. On the contrary, if the node is central in performing the computation, the eigenvalue will be large, positive or negative. So you can rank the importance of eigenvalues in a trained device by looking at their eigenvalues. And this motivates this technique, which we call spectral pruning, and which allows us to make the network compact. So to illustrate this, let me just take a simple case. So I will set the departure eigenvalues to 0, is a simplifying choice. And the idea is the following. So we want to aim at smaller networks. This is the way to go. So how we implement this? We decide a priori which is the percentage of nodes that we want to remove from a given neural network that perform its task. We compute the distribution of the eigenvalues. So the network is being trained, now is able to perform the task. You have access to eigenvalues and eigenvectors. You measure the eigenvalues and you study the distribution of the eigenvalues in absolute value. Then you decide a given percentile of the distribution, and then you cut. You just remove all nodes that have an eigenvalue smaller than the percentile that you have been choosing. And this is illustrated here. So this is the network that is working, and then eventually you say, okay, I cut out a number of nodes. How you rank the nodes based on the eigenvalues that you have been assigning through the optimization. So of course, the network gets smaller. And the question is it still working? The answer is, of course, yes. You have two strategies. The first strategy towards the smaller network is the following. So you train in reciprocal space, eigenvalues and eigenvectors, according to the recipe I told you before. Then you evaluate the eigenvalues, and then you prune the nodes. You remove the nodes, as I told you before. And then you end up with a smaller network. There is another strategy that I want to comment on because it's actually much more effective. And the strategy is the following. You train just eigenvalues. So you can handle very large networks, because as I told you, eigenvalues total in n, which is much less than n squared. Then you evaluate the eigenvalues, you trim the nodes, you prune the nodes, you compactify the network, and then now you train on the eigenvalues. So you have two strategies, and let's see the performances of this method. So here we report the accuracy of the device in carrying out different tasks. In this case, this is a different database as compared to MNIST. It's a Zalando MNIST database. So we are just classifying items like pants, shorts, shoes, or whatever. It's another database, nothing important. But basically, I'm cutting a different percentile. So when you move in this direction, you are removing nodes. And this is the accuracy that you get for the trimmed network. So if you check the green curve, which follow this strategy, then you can see that the accuracy stay unchanged. Also, if you cut about 90% of the nodes that you have been training at first. With the blue strategy, you can do also well, but you start seeing a drop in the accuracy at about 60% of the cuts. And if you try to do this in direct space with some recipe, which are widely accepted, and I won't comment on this unless you have questions, then you do much, much worse. So the claim is that indeed anchoring the training in reciprocal space opens up some perspective that is worth being investigated. I'm not claiming we have the final recipe. I'm simply saying that there are informations which are stored importantly in these collective parameters, which are the eigenvalues, and it is worth digging in this direction. Now, dynamics, which was actually my former title. So I come commenting quickly on dynamics. I'd like to bring dynamics into the game, because if the aim is to mimic brain is the dynamical object. We cannot just be happy with a simple optimization with very many parameters, even though we cut the number of parameters using these spectral techniques. So what's the idea now? The idea is that I have an input, number 4. I would like eventually to recognize this number 4, and I do this with a dynamical process. So I set a number of nodes, which could be in principle just the pixel of the image that you are supplying, and then I do not impose any topology a priori. I let the system to learn its own topology, and I run dynamically on the same set of nodes to perform the computation that should yield a number 4 if you provide as an input the number 4. So this is a dynamical system which has an attractor, and the attractor should be the right one if you want to categorize different images. So I'm trying to reformulate the problem as a dynamical process occurring across the network. And the idea is that I want to shape the network in such a way that the dynamical process is sculpting, is identifying different bases of attraction depending on the categories that you want to eventually recover. And to do this, we again use some spectral methods that I want just to briefly comment about, because it's in line with what I told you before. So this process that I explained in Word boils down to just an iterative map, which again is composed by two different steps. We have a vector, xk, and, as an input, a vector as an output, and we perform a linear transformation and a nonlinear filter, which is encapsulated in this function fk. So A so far is just an adjacency matrix, n times n is the size of the network, the number of pixels of the image that you want to analyze. And what is the hypothesis that I bring into the game for fk? Fk is a nonlinear function, and I need nonlinearities to shape the basis of attraction of the dynamical system I'm studying. But I assume that for large enough iteration, when k goes to infinity, this nonlinear function converges to the identity. So for large enough k, this nonlinear update rule turns into a linear system. And why I want to have a linear system? Because eventually I can impose that the linear transformation has attractors, has stationary solutions. And these are the stationary solutions I want to tend towards, and that I want to isolate for the initial step of the evolution by steering towards these attractors the different images that I want to eventually recognize. So before going to comment about the linear part of the update rule, let me tell you that for this specific application, we have chosen to deal with a nonlinear function that is shaped like this. So you see that for k large, this goes to the identity matrix. It looks like an arbitrary choice, and indeed it is an arbitrary choice, but later on we can relax on this, and we can actually impose a much more biomimetic approach to the problem we are studying. So it's just an initial choice to set the stage for the analysis. Now we focus on the linear transformation. Again, I write the matrix in terms of its spectral decomposition. This is the umbrella under which I'm operating. And now focus on the eigenvalues. I set small n eigenvalues to 1. And all other eigenvalues have a modulus which is smaller than 1. So this means that I'm imposing n different attractors of the linear update rule, which is the one that I eventually recover when k is large enough. So the attractors towards which the dynamic is eventually steered can be shaped at will. So these are the eigenvalues, the eigenvectors of the process, phi 1 up to phi n, and I can eventually, I go back, impose a priori that when you supply a 4, you get out a stylized version of the 4. So this is the eigenvectors relative to one of the attractors of the dynamics I'm studying. I can shape the final state the way I wish. And for k much larger than 1, then the update is linear by hypothesis. And so the attractors, these eigenvectors, for I smaller than n, are a stationary solution of the linear dynamics. So I have imposed n different attractors. What's the idea? I already anticipated this. I would like to act on the collection of tunable spectral parameters. So other eigenvalues, the ones that are not frozen to 1, and all the eigenvectors entries which are not frozen to the values that I want to recover asymptotically, all these form the parameters that you want to tune, and I want to steer a different input object towards different distinct target attractors, which are stably maintained also beyond the horizon of the training, and I will show this in a moment. So how you optimize the system? Now you have a dynamical system, you want to optimize the dynamical system. What's the idea? The idea is that you need, again, a loss function, and the loss function is constructed with these steps. So assume you have xk bar, which is the image of the input vector after k iteration, with k large, so that you are converging towards the linear update rule. Then you calculate the coefficients. You calculate the coefficients by applying phi minus 1. So you measure the coefficients along which the signal is aligned in terms of the governing eigenvectors. And then you focus on the first n entries, which are the attractors that you are studying. And then eventually you minimize, and this is the loss function, the square distance of the coefficients that you get with the target vector that is made of zeros except for the element that you want to eventually recover. So what I'm saying in complicated terms is simply that the system is evolving and you want the system to align along one eigenvectors. And you put this information into a loss function. The loss function depends on the spectral parameters of the model, and then you optimize the loss function. So in the end, in one sentence, the idea is to reach classification via sculpting the basin of attraction of a discrete dynamical map. So I'm trying to bring dynamics into the game by using the spectral decomposition of the linear update rule. I won't comment on this in details, but basically you can try to see with simple examples what is actually doing the neural networks in this representation. I told you that in general, neural networks are black boxes. You don't know what they're doing. If you focus on simple example, it is quite clear that now this dynamical object that we have been creating tries to identify separatrix between different basins of attraction. So for instance, here we have a database which is basically aimed at identifying numbers that fall inside or outside the unitary circle. So that's the task that you want to give to the neural network. And eventually, I don't go into details, but it's quite clear by looking at the dynamical evolution of the system that the dynamical network tries to segment the separatrix that is dividing the two basins of attractions for the two attractors that you impose into the dynamics of the system. So that's the idea. You can visualize this in simple examples, and then you can try to see how the system performs back to MNIST database. So you supply 4, and then eventually you get 4 out of this. This is the eigenvectors towards which the system is converging. The same for 5. You see that is you have a successive approximation that bring the 4 into evidence out of the very many different attractors that you might have. When you recognize the number 4, the coefficient relative to the 4, the orange one jumps to 1, and all other are down to 0. Vice versa, if you supply a 5, the green coefficient, which refers to the eigenvector 5, converges to 1. You are aligning along this direction, and all other are going to 0. This is the accuracy of the method, and you see we are training up to this iteration, but after this iteration, the accuracy stays unchanged, and this is written trivially into the dynamics that we have formed. On the other hand, if you try to do the same with conventional neural networks, this is a recurrent neural network, which is trained at iteration 5, epoch 5, as it is called. Well, it is performing quite well, same score as compared to ours, but you add one iteration and then everything drops to 0. Sequential learning. So I told you that standard neural networks are very bad at dealing with sequential database. So if you learn one task, then the memory is completely washed out when you try to learn the second task. So we tried this. This is what you get with the standard neural network. Still, we're playing with the same data set, digits from 0 to 9. We divide the numbers in 2 different subsets. Those with numbers ranging from 0 to 4 and the other from 5 to 9, respectively red and blue. So in this case, we first train the network to deal with numbers from the first set, from 0 to 4, and the accuracy is quite large. But then when you try to teach the network to recognize the other numbers, then you see that the red curve dropped to 0, and the network learned to do the second task at the detriment of the first. If you instead use this dynamical approach, you have memory kernels, which are the eigenvectors, and with some drop that we should be trying to improve, but eventually the neural network in its dynamical version can cope with both data sets simultaneously. And this is the direction that, again, it's worth investigating. Nothing final, but direction for further thinking. Another point that I want to make, and then I will stop, basically the last slide. It's again a direction that we are trying to explore. So far, I told you that you can form maps, basically, which are nonlinear. The nonlinearity eventually fades away, and then you converge to a stationary stable fixed point, which is the eigenvectors that you have embedded into the dynamics. Indeed, the brain, at least to my knowledge, works with time-dependent signals. So I don't want to go towards a stationary stable solution. I want to recover a time-dependent signal. And you can actually do the same, play the same trick eventually. What's the difference? The difference is that now eigenvalues are not set to 1, but they are complex numbers. And with these complex numbers, you can have limit cycles with different periodicity. And so you can approximate any time-dependent function which are produced at the observation node. And actually, you can also confine the nonlinearity in a subset of nodes, so you can remove this artificial choice for the nonlinear function that I made before by having a sort of a more realistic version of the whole scheme. So I can just go to conclusions, sum up what I told you. Spectral learning provides a new angle to neural network training. Interestingly, it's fully integrated with standard machine learning software. So Keras, PyTorch, if you want to play with this, you can just use the standard machineries, just add the spectral layer. you can trim or prune the network by using the eigenvalues. And we're studying the dynamical approaches to classification and regression with rules which are non-Hebbian, so global rules. And I have to thank a lot of people that have been contributing to this, and in particular Benedetta, who's sitting there, and I see that she's shy, and that's why I'm insisting on this. Okay, so thanks a lot.
Questions or comments? So I would like you, oh, sorry.
What about recurrent neural network? Because these are feed-forward, no?
Yes.
I don't know if you have some idea or application with recurrent.
Actually, this is a comparison with what this picture, and this other picture. Sorry, this other picture is a comparison with what you get with recurrent neural networks. So in recurrent neural networks, you basically have stacks of layers which are all identical, and then you map input and output with the same adjacency matrix. So in this way, you form a sort of a dynamical system. But then, for instance, they cannot cope with this simultaneous or sequential handling of data set. And as I tried to show you before, they are bound to the epoch of the training. So they are very good if you stop, if you check the performance of the machine at the epoch of the training. So this is the epoch where the optimization was performed. But if you try to go beyond this in the spirit of a dynamical system, then the accuracy drops away. So, I mean, okay, it's trivial in a way, because I've written into the system that I want to have a stationary stable equilibrium, but I think it's an ingredient that you should have into the model if you want to mimic at something that has in mind the brain, if you allow me for the joke.
So can you comment on the number of nodes you need on the RSN with respect to the number of nodes you need before and after pruning?
Actually, this depends pretty much on the task that you're studying. So for this specific task, very few nodes. So I could say 15, 20. It's really, really, really small. It's really, really, really little. Yeah. I didn't understand.
I mean, pruning mechanism, how different it is from dropout ratio in terms of performance.
I really don't understand a single word. If you
how different this pruning method compared to dropout ratio, dropout mechanism which you have in TensorFlow or PyTorch, because usually in PyTorch or TensorFlow you can stack dropout layer. But different here, you try to implement smart pruning in dropout. Usually, you just randomize randomly, or you cancel nodes, which is less active.
I mean, we tried this, and I mean the paper that reports on these findings. We have all these comparisons. I don't remind exactly the results, but I mean we can check the paper together if we wish later. But basically, I mean the overall idea is that it's a complementary approach. I'm not saying that this will beat whatever else you have in mind. It's a complementary approach which enables, at least I think, us to show from the fundamental point of view that there's something interesting into the eigenvalues that deserve to be further understood. So I'm not saying that this is the final recipe for pruning that everybody should be using. It's effective, it works. If you are naive, and here I've been a bit naive, you do much better. But then if you go for more sophisticated approaches, then okay, equally good. I mean, up to you to choose whatever you want to choose. But actually, that's an alternative. And I more than to advertising the alternative, I'm interested in trying to focus on the fundamental aspect that might be hiding behind the spectral version of the training.